Hello, let's talk a little bit about ray diagrams and geometric optics. This stuff is going to be related to plane mirrors. We'll focus later on spherical mirrors and lenses in future screencasts. But this is just kind of talking about the basics. We're talking about light as though it's going off in a straight ray. And so we ask kind of what happens when it hits a surface that it reflects from, or a surface that it passes through and bends, or crosses any number of things. Right now, though, it hits a reflective surface. And the law of reflection that we're going to use is that the angle of incidence, theta in, is equal to the reflected angle, theta out, or the angle of the incident ray and the outgoing ray, how I kind of think about it. Theta we use kind of just to represent any old angle. And theta we're going to measure is the angle the ray makes with the normal. So, that all is a whole bunch of words. Let's deal with some pictures. Consider this. Here's my mug. Here is a mirror. You can tell because it's a straight line right now. And so this is a ray of light leaving my mug and traveling to the mirror. It makes some angle with the normal, which we're going to call theta in. So the normal is just this line we draw perpendicular to the surface. That's kind of the mathematical definition of normal. Which, I mean, may be thoroughly disappointing to some people, relieving to others, but it is what it is. And so what this law of reflection would have us think is that there will be a reflected ray that goes out, and I wish now I guess it's going to be going out to here. It will leave the mirror traveling at the opposite angle. Oops. You can't see my ruler, which is what's making this really complicated. So I'll be traveling outwards like that, making some angle theta out with the normal. And these should be congruent. That's kind of the point. So now that's all well and good. Oh god, sorry. It occurs to me that dropping things onto the computer where the microphone is may cause horrible damage. At least to your ears as you listen. That might have been really loud. So now the reason that we do this is to try to locate the image of this object in the mirror or outside of the mirror. That's why I'm trying really hard to draw these lines as straight as I can. It's not having it. It's going to be close enough. Alright. We're going to draw two rays to locate this point. So here is ray 1. Here is ray 2. Ray 1 went out this way, into the mirror this way, and then out of the mirror here. Ray 2 is going to go straight in, and this is totally perpendicular, and then straight out. So these two rays are not going to intersect on the real side of the mirror, where the object is. If I extend them out forever, they simply move away from each other. So what I need to do is extend them into the mirror, where they will become virtual rays. The reasoning behind this calling them virtual is that there's not actually anything inside of the mirror. It's not like an Alice in Wonderland kind of thing going on. And so where they intersect on the other side of the mirror, this is the image, the location of the image at least, of my object from over here. And so what we want to do really is repeat this for a whole bunch of points and just keep doing it again and again until we finally arrive at a location of the image overall. We've described it completely. So we could, for example, send this out. Turns out this straight ahead ray is always a good one to draw. I swear, drawing straight lines is something that I can do. I just choose not to. You should not make that choice. It would be wise for you to learn how to draw straight lines. The stylus just has a weird kind of interaction with this. Makes it a little trickier than it needs to be. And 2 down. You'll notice the reason that we're doing this on grid paper is because it helps. I don't have to bust out a digital protractor of some sort. I can just sort of count boxes and go over. Or pretend like I'm counting boxes, and in fact just kind of draw them randomly and hope that it works out for the best. So again, theta in, theta out, supposed to be quite equal. And I shift the whole image to the left a bit, not helping anybody. And I extend this back. So things that we should note, this is 1, 2, little less than 3, 1, 2, little less than 3, same distance. This is 1, 2, 3, 4, 5, 6 and a bit, 1, 2, 3, 4, 5, less than 6. Awkward. Probably did not do the best job drawing, or counting maybe? We're going to blame drawing for that one. Should be over here. So there's always going to be a little bit of fuzziness with this. The diagrams are really a way to help us arrive at a second version of these answers. We're going to get a little more into kind of the quantitative numerical view of it later. But for now, try to draw straighter lines than I am. Let's look at one more example. Here we have a cat on a slide. We want to kind of go through and just try to locate these points one by one. We're going to try really hard to do it well. And didn't actually draw anything. Alright. We know that's going to have to get extended. So there's one. Draw this one. Oops. To there or so. And probably extend it would be a good idea. This is really much harder than it needs to be. Sorry, I really should try to chat or something to keep this interesting. There are some interesting... Whoa, that's... We're just gonna kind of go with that one. So you'll notice some things about this. We always draw, since we have to draw two rays, one of the rays we draw is always the one that goes straight in. Stop me if I said this already. You can't. Sorry. Bad joke. We do that one because it is a nice and simple one. We know that it's always going to go straight in, always going to go straight out. And so we don't have to worry about whatever kind of nonsense might happen. We don't actually have to do really any work with it whatsoever. We just get to draw it and, you know, figure it out. Yeah, that's totally not how far apart those are. Well, this should be an interesting picture when all is said and done. Oop, already used that color. So, again, it's always draw two rays. One goes straight in and straight out. The other one, we just kind of pick a spot. You know, you want to pick something that's not going to be too terrible to draw. Ideally, your graph paper is not obscured by the random cat picture that you put into it. And so you don't have to just totally guess where these things go. Turns out that totally guessing is not the most accurate way to do this. I realize that may be shocking, but, you know, never let it be said that nobody told you that. Guessing has its own kind of risks. Yeah, I have no idea what this picture is going to look like in the end. It's going to be hilarious, though, I bet. Now, as you may be getting and you may be noticing now, doing this for literally every point in the picture would be time-consuming, prohibitively so. So what we want to try to do are notice that there are some trends here. As we may have recognized from looking into mirrors before, we know that the size of an object in the mirror is roughly maintained. We know that the distance into the mirror that the image appears to be seems to be pretty much... Yeah, nope. This is going to be silly looking. We know the distance into the mirror is basically the same as the distance it is in front of the mirror. So you appear to be as far into the mirror as far behind the mirror as you are in front of the mirror. And we know that the image produced is upright. It turns out that all of these traits are related to some equations that we can work out for mirrors. So all of these relationships are quite easy to kind of explain from an equation, and thus when we look to find more complicated cases, those same equations will help us sort out what kind of things are going on. They won't help us draw accurate pictures, however, which is unfortunate. I don't even... That's just very confusing looking to me now. We're almost done. And then we'll create this terrible monstrosity and try to sketch it out and connect all the dots. I apologize in advance. This is going to look absolutely ridiculous. I feel like this is like a very bad version of there's a monster at the end of this book. You just keep waiting for it, and all you're going to get is this horrible, hideous apparition of a cat picture, which bears no resemblance to a cat on a slide, even though that's clearly what I'm trying to, like, trace here. Alright, so... these are the top of the slide. These are the bottom of the slide. And I guess it goes something like this. And somehow there is a whole cat in here. Important to note that the back of the cat, the cat gets flipped left to right. It's just rough. Hopefully your drawings will be slightly more artistically inspired than mine. If not, at least you know that you're in, good company with me. I can't do it much better. Hopefully this helps you kind of piece together what this should look like. I seem to have lost touch control, so all I can do is kind of scroll through the notes again. Taking this idea of, incident rays and outgoing rays, they should, on a flat surface, on any surface really, they should always have ingoing and outgoing angles are equal relative to the normal, and we can locate points of our image by drawing two rays from any point on our object. So if we want to locate something more complicated, we need to locate a whole bunch of points. Unfortunately, small errors in making straight lines can lead to catastrophically small cats. So exercise good caution when drawing your own diagrams. Good luck!